Hey class. Sorry for the late video. This week has been a little crazy and I've been a little sick at the beginning of the week, but I'm feeling better mostly. So I'm gonna lecture through Unit 7. I'm going to share my screen. Unit 7. So last week we talked about hypothesis testing for single samples when the population, move me out of the way, standard deviation is unknown, right? We learned how to estimate um, standard deviation. And then we learned how to calculate t-scores. And then we used our SciStat calculator to calculate probabilities under the t-distribution. So this week, we're going to learn, now that we've learned how to estimate known parameters and test hypotheses with a single sample, we're going to learn how we test hypotheses about two independent samples. So for example, we wanted to test the efficacy of a new memory treatment where N was 8 participants. They're randomly assigned to one of two groups where there's a treatment or there's a control, right? The group that gets this intervention or something happens to them, or the control group where nothing's happening to them. And then they're given a memory test afterwards. Does the treatment group score significantly higher than the control group? To answer this question, we want to measure the effect of the treatment, right? We need to see at the end of the day, both of these groups took the same test. Did the group that did the treatment, did they get a significantly better result, right? Was their memory improved? And so we have some math down here, right? We see some statistics, but what do those numbers mean? So x1 is 50, x2 is 45. The means are different, but are they significantly different? So we're going to turn this wordy question into a stats question and figure it out. So effect size is a measure of the magnitude of an effect, right? So if there was some effect, if there was some difference in the memory scores, if my treatment had some effect, what was the magnitude of that effect? Was it significant or was it not? Was it meaningful or was it just probably due to some variance in my population or the day or the time or individual differences, something that I couldn't say was attributed to my memory improvement group. So we use something called Cohen's d to look at effect size. So the formula is d equals the difference between the means divided by the standard deviation. So the difference between the means looks like x bar 1 minus x bar 2, right? The difference between them, subtraction. But the problem is that we have two standard deviations. So you can't just divide by these standard deviations. So we have to do something called pooling. So pooled standard deviation is a weighted average from the standard deviations of the two groups, where their weights are determined by their relative sample size. And you'll remember that degrees of freedom are our number minus one. So this is really, really close to our sigma hat that we had. So previously, you can see that formula down here. But looking at this, looking at our weighted standard deviation, we have sigma with the hat-ish, and it has a little p for pooled. It's equal to the square root of sum of squares 1 plus sum of squares 2 divided by degrees of freedom 1 plus degrees of freedom 2. So let me move me out of the way. Looking at our treatment group over here with our x bar 1 is 50 and SS1 is 250. And our control group where x bar 2 is 45 and SS2 is 184. And we put that into our formula here, we end up with 8.50. So now that we have our pooled standard deviation, we can do our Cohen's d formula. And we find that we get a Cohen's d of 0.59. Well, what does that mean? Let's look. Cohen's d recommends the following guidelines for interpretation. So when d is less than 0.02, there's a small effect size. If d is between 0.21 and 0.8, we say there's a medium effect size. But if d is larger than 0.8, we say the effect was really large, right? That's like saying something significant when we're talking about p-values. Not exactly the same, but similar, right? That's meaningful. So for our example, we had a Cohen's d of 0.59, which means we have about a medium effect. So that's good information, but it still doesn't tell us if it's statistically significant, right? Significant. It says, well, there was some pretty moderate effect here, so maybe it's significant. So maybe we should do an independent samples t-test. So remember, when we're doing hypothesis testing, we have to define two competing hypotheses. The null, referred to as the H0, and the alternative hypothesis, referred to as the H1. And we always assume the H0 is true, right? We always assume the null is true. So we're always looking to fail to reject the null, right? We're assuming it's true, so we are always looking to fail to reject it. We don't want to reject it because it's true. So when we find significance, then we fail to reject the null. Compute the probability of observing our data if the null is true. We're going to convert our data to a t-score and then find the probability of obtaining that observed t-score or a more extreme version. So we're going to say mu1 is the population mean of the treatment group, mu2 is the population mean of the control group. Then we're going to define our null and our alternative. So our null hypothesis says that mu1 is equal to mu2. There's no difference between the two means because we're saying there was no effect. So our control group's mean and the treatment group's mean should be exactly the same, no statistical significance. Or alternatively, H1 says, our alternative hypothesis says that mu1 is greater than mu2, right? Our treatment group had a higher mean than our control group. And we're going to assume that the null is true. Now we got to compute the t-score. So, and our t-score here, move this out of the way. Everything's in the way. The general form of the t-score is t equals sample mean minus population mean divided by estimated standard error divided by the square root of sample size. So specifically, that looks like this down here, broken down, right? T equals x bar 1 minus x bar 2 minus mu1 minus mu2 divided by estimated standard deviation pooled divided by the pooled divided by the square root of 1 over n for our first group plus 1 divided by n for our second group. That's a lot, right? Just take a second, screenshot this, write this down, but this is how we can compute a t-score. Those aren't n's. That makes more sense. I'm sorry. Working through my illness. Down here, the bottom of this formula, let me repeat that. Sigma hat pooled the square root of 1 divided by mu1 plus 1 divided by mu2. Sometimes the n's and the mu's throw me off, but that is not an n, that's mu. So if the null is true, meaning mu1 equals mu2, we then have t equals this formula. So for our numbers, right, we have 50 minus 45 minus 0. And then we have 8.50 times the square root of 1 divided by 4 plus 1 divided by 4, which gives us 5 divided by 6.01, which gives us 0.83. So if we put that number in SciStat, we're going to choose the t distribution. And remember that we have to put in degrees of freedom. Well, we have two different data, or two different participant pools, or two different n's. So we're going to take degrees of freedom for 1 and degrees of freedom for 2, which is what? Our number minus 1. Well, we have to do that for each one. So we end up with 3 plus 3, which equals 6. So it's like almost like a pooled degrees of freedom as well. We're choosing the upper tail, right? Because we're saying that it's higher. And then when we put it in A, we get a t-score of our t-score is 0.83. So that gives us 0.219. The observed data is plausible if the null is true. So we fail to reject the null and conclude that the treatment group does not score significantly higher than the control group. So the null is true, but I know that's worded weird and that's confusing. We fail to reject it. That means that we're not rejecting it, right? So we're accepting it because we're saying that there was no difference. And I know that's really wordy and takes a second, so just think about it, right? Hopefully you've gotten the concept of when we reject and when we fail to reject. But the alternative we don't really talk about, right? We're never trying to prove the alternative. We're never trying to find support for the alternative. The alternative is like Fight Club, right? We don't talk about Fight Club. First rule Fight Club, don't talk about Fight Club. We don't talk about the alternative. So we just talk about the null. So we either fail to reject the null or we reject the null. So because this 0.219 is much larger than our 0.05 threshold, then we know that we cannot reject the null. So we fail to reject. Watch it again. If you need me to repeat it, just rewind me and play it again. But that is it in a nutshell. So just watch it a few times and let me know if you have any questions. Let me stop the screen and get us out of here.